Hey, everybody, come on in. Feel free to ask me any questions while we're waiting for the other people to get in. Still not very many people here. Anybody have any questions? All right. Well, we're kind of a little bit in a bit of a rush, so I'd like to go ahead and get started. Uh, last time we started into chapter 9, I gave you more or less a good fraction of the equations that are necessary. The only thing I really didn't define was the impulse, and we're going to work an example today where we use that, and I'll use that opportunity to tell you exactly what the impulse is. It's not that big of a deal. We usually use the symbol J, capital J, or sometimes people will use a capital I. There's problems with both of those. Capital I is often used for current. Capital J is often used for current density, all sorts of stuff. So I'll probably avoid using necessarily a symbol, but I'll just tell you what it is. So we'll run from there. So let me go ahead and start off by sharing my screen with you guys so that we can get started on working some of these examples. I think when this is all done today, you'll have plenty of examples to allow you to start making headway on the homeworks of chapter 25. But chapter 25 homework, the conceptual I'm going to be okay with being due Sunday, but the actual problems I want them due no earlier than say Wednesday, or excuse me, but Tuesday night. Since we meet on Mondays and Wednesdays, so that's the battle plan. So even if you don't see it move, just know that the chapter 20 or excuse me, chapter 9 homework problems, the actual problems will be due Tuesday night around 11:59 p.m., whereas the conceptual might be due Sunday. Okay. So I basically mirrored what your author did in problems. I sort of made up my own problems with different numbers, and I sort of worded them a little differently. I just sort of remembering what we cover. So in this first problem, it says a typical tennis pro can serve a 0.060 kilogram tennis ball at about 62.0 meters per second, which is about 140 miles per hour, even though the strings only touch the ball for about 4.2 milliseconds. How large is the average force exerted during the serve? Okay, so that's the problem we're going to attempt to solve. Here's my solution. So what we know is Newton's second law says the summation of the forces is equal to dp dt. And as I told you, P for a single object can be listed as P is equal to M times V, or of course, if it's a system of objects, then it'd be the summation of M sub I, V sub I, where V sub I is the vector of each mass. In this case, we're going to use something sort of like it. Specifically, we're examining the actual strings of a tennis racket striking a tennis ball for a small period of time. And during that period of time, the force is going to be quite large. The ball is going to initially be not moving because when you actually serve a tennis ball, the ideal scenario is you're supposed to throw it up, maybe into the court a little bit. And then at its highest point is when you're supposed to be swinging so rapidly that your momentum and the force with which you're swinging the racket lifts you off your feet up to strike the ball with the strings of the ball, with the strings of the racket, and then you hit the ball while it's essentially sitting still and fall into the court. So that's the scenario we're going for. That force is so large that all the other forces are going to be irrelevant. So you can ignore, for instance, air resistance, and you even can ignore the weight. So with that in mind, we can say the average force of the serve, and we're all going to treat it as if it's one dimensional. So I'm just going to put an average there and not even talk about it being a vector anymore, because in this case, we're actually just talking about one dimension. So the average serve is going to be delta P over delta T. That's the average force. Excuse me, I said the average serve. That's the average force that should be acting on it based on Newton's second law. So delta P, which is supposed to be P final minus P initial, and in this case, like I said, we are talking about one-dimensional motion. So really, if you want to talk about it being a vector, then things moving in one direction are going to be a positive momentum, and things moving in the other direction will be a negative. I cannot get this. Oops. There we go. I just screwed up. I was trying to get the chat to be turned on so that we can keep an eye on that, but instead I accidentally turned off the whole stupid thing. So now I got the chat back. Yay for me. And now I got to get my screen back. Yay for me. Why are you being a pain in the butt? There we go. Okay. So it looks like it's finally doing it now. Okay, so as I said, this is a vector quantity, but we're dealing in one dimension. So I don't have to worry about it. I'm going to say the initial momentum is 0. The ball might actually have a little initial velocity, but it's really not going to be anything compared to the 140 mile per hour serve we're going to be hitting. So in this case, what we're going to get is 0.060 kilograms is the mass, and 62.0 meters per second is the velocity. That minus 0 is going to give us, let's see, 0.06 times 62. This gives me 3.72. And notice the units are kilograms, meters per second. Another unit for momentum, by the way, would be a Newton second. So that's acceptable as well. So just in case if you need it. So now that we have that, I need to take into account the time. So according to this, it says that the ball is in contact with the string for a mere 4.2 milliseconds. So the average force of the serve would equal delta P over delta T. And the delta P we already found was 3.72 kilograms meters per second, which again, I could have written that as a Newton second. So when you divide it by a certain number of seconds, I think you'd see that it just comes out in Newtons. That's another reason why I brought it up to you. So in this case, it's 4.2 times 10 to the negative 3 seconds. So when I divide that, I get 4.2 10 to the negative 3. This gives me 886 roughly newtons. Okay, now that's one extra sig fig than I'd actually intended to use, or that's actually justified in using, but I wanted to give you some idea what that was. Now, that's actually a pretty good size force. I think you guys recall that a Newton is about a quarter of a pound. Let me give you an idea what this is in pounds, and I'll even make an estimate of roughly how much weight in kilograms a person could weigh such that this hit would be big enough to pick you up or to pick that person up. So in this case, I'm going to start off with 886. And now I'm going to talk about, I want to change my units. Let's see, the unit of force is what I want here. And there's my Newton. So 886 Newtons. I'm going to add to that 0 pounds of force, and that's going to give me, in fact, on the order of 200 pounds. Okay. Alternatively, I can take 886 and divide it by, I can take 886 and I can divide that by 9.8. And that gives me 90 kilograms or 90.4 kilograms. So another way of looking at how big this force is by saying that, oops, I just erased everything. this force is large enough to pick up a 90 kilogram person. So that's a pretty big deal. So just to give you an idea of roughly how big that is, I thought it'd be nice to put that Newton measurement in context. Anybody have any questions about that? Okay. All right, so we've basically got that. No questions on this particular example. Sorry, I'm a little distracted because I've got people logging in and then logging back out and all sorts of stuff. So I'm trying to figure out what's going on. So let's look at another example. This is a case where it's not so obvious that anything we've learned has any relevance whatsoever. It says a water hose delivers about 1.9 kilograms per second of water, while the water leaves the hose at about 22 meters per second. Assuming that the water hits a car that is being washed and then stops, what force is exerted on the car by the water? Okay. So I want you to again think of our Newton's second law, and I'm going to work it out that way, but I'm going to make some use of something. So for starters, I'm going to say that the flow, which I might label the symbol phi, is equal to 1.9 kilograms per second. That's kind of helpful. Basically, if what that means is if I took a hose and I stuck it in an empty 5 gallon bucket, for instance, and I let it run for exactly 1 second, then I would could weigh that water and it'd weigh 1.9 kilograms. We also know that the velocity of the water is equal to 22 meters per second. So that's pretty fast. So what I'm going to do here is imagine that the end of the hose maybe looks like this. Okay. And has, let's say, some area A. Not that I'm necessarily using it, but what's going to happen is the water is going to spray out like this. Okay. And then it's going to hit the side of the car and come to a stop. So initially, we're looking at a particle of water moving at 22 meters per second, and that's going to be V initial. And then all of a sudden, V final is going to be 0 meters per second. Okay. Now, what we know is the summation of the forces is equal to dp dt. That's Newton's second law. Okay. I'm going to ignore the fact that some of this water may actually arc downward, make it a two-dimensional problem. We're just looking at it as if the water hose is close to the side of the car. It's going to shoot out horizontal and then come to a stop. Therefore, it's all again one-dimensional. So that makes it kind of nice. We can actually interpret this again, realizing that the only force that matters in this particular problem for this small amount of time really is the force that the car is going to exert on the water, which happens to be the same as the force that the water is going to exert on the car, but in the opposite direction. So I'm going to go ahead and say, let's let this be an average force. So average force is going to be equal to delta P over delta T. Well, here's something interesting. If you actually take the 1.9 kilograms per second, that tells you how much water is being delivered every second in kilograms. So if you looked at, for instance, 1 second of time, we could possibly say, okay, this is t equals 0 seconds, and this is t equals 1.0 seconds. And what we're doing with this is we're realizing that this distance, which is 22 meters, is the distance that that one particle or that 1 kilogram, for instance, of water would travel. Or in this case, it'd be 1.9 kilograms would travel. So you can sort of think of it that way. When you start to think of it that way, then you realize, okay, well, I can sort of think of this 1.9 kilograms as the mass, and then the momentum, of course, would be the mass times velocity. So if I went ahead and multiplied it by the 22 meters per second, I would get basically kilogram meters per second, which is a unit of delta P, or P, that's the unit of momentum, divided by the time taken. So in fact, this is exactly what we want. We can literally get kilogram meters per second squared, which is the unit of force. And in this case, it's going to be 1.9 times 22. That gives me 41.8. And that's one extra sig fig again, but that's 41.8 kilogram meters per second squared, which is exactly a Newton. Okay. So this is one of those cases where the units sort of worked out for you. But another way you could think, if you didn't want to think in terms of the units, that feels like it was a little too, oh, wow, lucky Mr. Younger. He happened to multiply and got the units that he wanted, so he assumed the right answer. That's not exactly what I'm doing, but I could totally see how you're making that conclusion. It seems perfectly reasonable given what I actually told you and stuff of that sort. What you might want to think about is if you look back at this column or this cylinder that I just did, obviously 22 meters is not the kind of distance that water is going to spray without leaking or without dipping in the y direction. So this is sort of apocryphal at the beginning, but if you imagine how much would hit in 1/100th of a second, so imagine delta t equals 0.01 seconds, then what you're going to see is here's the end of the water hose. And now out comes the water. And I'm exaggerating still how big this is. But now what we're talking about is this distance right here is 0.22 meters. So maybe it goes about 22 centimeters basically. And this is t equals 0 seconds. And this is at t equals 0.01 seconds. With that in mind, this is 0.019 kilograms of water. And during that time period, we're basically going to take 0.019 kilograms of water, and that was going a velocity of 22 meters per second. And that means its momentum initially is equal to 0.019 times 22 gives me 0.418, carrying one extra sig fig, of course, 418 kilograms meters per second. Okay. So that's the initial momentum. Of course, the final momentum, P final, is 0. So delta P is equal to P final minus P initial, which gives me 0 minus 0.418 kilograms meters per second. That's going to be delta P. But F average, I'm trying to show the bar on top as the average, not as a vector symbol. So the F average is supposed to be delta P divided by the time taken. Well, in this case, the time taken was 0.01 seconds. So I'm going to say at 0. Or negative 0.418 kilograms meters per second divided by 0.01 seconds. So when I divide that, I get negative 41.8 newtons is the average force, and maybe that makes a little bit more sense to you. That's certainly fine if that's the case. Any questions on that? All right, so that's a lot more stuff than I would normally put into such an example. But you can read the book's example. He makes which is very much like this one. He makes a different argument than I do, but both of them are really good. So find the one that you like and keep it, or actually remember both of them, and that might help you further later on. All right, so now we're moving on to conservation of momentum. So this problem is actually going to require us to apply conservation of momentum. So I'm going to reiterate exactly what that is. But let me start by reading the problem. It says two identical trains, and I mean train cars. I really should have written in there train cars, are on the same track, but one is moving at 6 meters per second while the other sits still until it is run into by the original one, by the first one. Oh, I just realized how horrible my dot on my eye is here. Ugh. Give me a, okay. Sorry, I know this didn't matter to any of you, but I just saw it and it just got in my crawl there. Okay, so two identical train cars are on the same track, but one is moving at 6 meters per second while the other one sits still until it is run into by the first, which is a much better wording than other. When they collide, the two 12,000 kilogram cars stick together and roll away. What is their common speed after the collision? So conservation of momentum and the law of conservation of momentum says when the net force acting on a system is zero, then momentum is conserved. And the reason why that's the case is Newton's second law says the summation of the forces, in other words, the sum of all the external forces acting on the system. So I'm going to put SYS on there just to remind you that we can use Newton's second law for a single particle, or we can use it for a system. So there's the system there, is equal to dp dt. Now, what I'm treating as the system in general could be two masses, like the masses of these two train cars, for instance. That'd be fine. Now, if the summation of the forces on the system, the external forces on the system, is equal to zero, then dp dt is equal to zero. And of course, what kind of function has a derivative that's equal to zero? So think y equals something. The derivative of this y function, which could be a function of x, for instance. That's right, Julio. So the y could be a function of x, but since the slope we know, or excuse me, since we know the derivative is the slope, what objects y equals something, some function of x, what functions like that have a slope of zero? And as Julio said, yes, it's a constant. So this implies P, which is a vector quantity, is equal to a constant. And that is the very crux of conservation of momentum. Conservation of momentum says that the momentum that it has is a constant, period. Okay. So with that in mind, we could say, for instance, two train cars, MA VA plus MB VB is equal to MA VA. I'm going to put a prime on it to represent the velocity of a car after its collision, car A, that is, plus the mass B times the velocity of car B after the collision. So I'll put a prime on that as well. So that really is the vector statement of conservation of momentum. Okay. So that's the actual law that states it. In this case, I'm going to go ahead and draw out what we have. We have P initial And I'm talking about a system here, so I'm going to go ahead and realize that on a railroad track, it's basically just one-dimensional motion. Nothing's going to go left, go right, go up, go down. So we just have that. And it's the momentum of a system, so I used a capital P instead of a lowercase p, which is often what I do. So the initial momentum, in fact, is 20,000 kilograms. That's the mass of one of the train cars times 6.0 meters per second. And I'm going to assume that that first car is going in the positive coordinate direction. So that's why I put a positive there. The other car also has a mass of 20,000 kilograms because they're two identical train cars. However, the velocity is 0 meters per second. So you can see that this is going to be 120,000 kilogram meters per second before the actual collision. Okay. Now, P final, again, using an uppercase, P final has the two stuck together so that their mass is that thing's mass is 20,000 kilograms plus 20,000 kilograms like that times V prime. Notice I didn't label it VA or VB. I just labeled it V prime because, in fact, A and B are stuck together, so they're all the same velocity. So conservation of momentum tells us that PI is equal to P final. So with that in mind, I'm going to say 120,000 kilogram meters per second is equal to 40,000 kilograms, because that's what 20,000 plus 20,000 is, times V prime. So that gives me that V prime is actually equal to 3.0 meters per second. Notice that's half the original speed. Okay. So we doubled the mass, but expected the momentum to carry on as if it's twice as heavy now. If you wanted the exact same momentum for something that's twice as heavy, since P is equal to M times V, if you double M, you're going to have to cut down V by a factor of 2, and that's exactly what happened. So this conservation of momentum is part of the problem why it's so hard. If you, assuming you guys have done this, have you ever run beside a skateboard and tried to jump on it while it was rolling? Or alternatively, at the beach, have you ever tried to run and jump on a skimboard and try not to fall? Both of those are a little bit problematic. The reason that, well, in my opinion, the reason that they're problematic is when you go to jump on a skimboard, for instance, even if you know a little physics like I do, you're probably going to think, okay, well, I'm not going to necessarily exactly match the speed of the skimboard, but I'm definitely going to maximize or maximally increase the mass of the system because I'm going from probably a skimboard that maybe weighs 2 or 3 kilograms to a skimboard plus fat Mr. Younger that weighs 110 kilograms. So and that's wishful thinking, but you're looking now from going from, let's say, 4 kilograms to 105 kilograms. So I'm clearly going to tend to either slow down or speed up the skimboard by quite a lot. So if I jump on it and don't exactly match the speed, then a drastic change could occur. And that drastic change is either going to cause me to fall off the back and shoot the skimboard out and, God forbid, catch somebody's ankles, or, you know, coordinated me is going to flip over forward and, break my neck. But the same thing happens with skateboards as well. If you ever try to do that, in fact, I told my students today, a very young memory I had was like it was like the same day or maybe 2 or 3 days after I'd learned how to ride a bike. I was, sort of showing off riding down the street and popping wheelies and cool stuff like that. And I was riding with my friend who was towing a skateboard behind his bike on a rope. So I just had this wild idea. Hey, I wonder if I could just like take and pop a wheelie and lay my front tire down on the skateboard and then just coast with this guy pulling me. I was like, this will be great. it was not great. It was really a horrible thing because I don't remember what happened. All I know is I went to set my tire down, and then there was metal in the air and there was a smell of blood, and I tried to stand up and I couldn't, and I finally got up and tried to scream because my parents I wanted to help. I thought I was dying because I couldn't breathe. I was going, but evidently I landed, but knocked my wind out. And if you ever knocked your wind out, it's really exhausting. But to make matters worse, my parents had already called me. We were getting ready to go somewhere, and I guess they were showing me a lesson by leaving. So they drove off with the in the Jeep with the top off, looking like this fun family, wee, riding down the road, and I'm back here, ow, ow, couldn't see anything. So, anyways, they were gone for 30 minutes. Luckily, my breath came back, and I did not die, as you can see. But anyways, be careful with that. Anybody have any questions on this problem? Well, I don't know y'all how y'all aren't having as much fun as I am, but I'm just telling you, I'm having a good time. Okay. All right. Here's another problem. And again, this one's very much like one of the ones your book has. It says a rifle has a mass of 7.0 kilograms and fires a projectile of mass 0.0300 kilograms at a speed of 735 meters per second. What is the recoil speed of the rifle? So this is one of those things, recoil, which if you've ever shot a shotgun or a rifle or a handgun, you know that this recoil thing exists. For instance, if you fire a handgun, it's not uncommon for you to fire and feel it go like this. If you're firing just a rifle, you don't feel hardly any kickback. But when you fire a shotgun, sometimes you can feel a significant kickback. That's called recoil. And what's going on there is a conservation of momentum. You have initially a system. That system is made up of a rifle and a itty bitty bullet inside the rifle. Okay. Now, when you pull that trigger, just before you pulled the trigger, the bullet nor the rifle were moving, if you assume you're standing still. So the total momentum of the system is zero. Then when you pull that trigger, this little thing comes in and it pokes a dent in the back of the casing of the bullet. It's like a shell casing. If it's a shotgun, for instance, it's literally like a bit of brass with a buttload of gunpowder in it, and that's going to cause an explosion. And luckily, the brass or the metal around the shell, combined with the strength of the inner part of the barrel, prevents that shell from blowing up in every direction, because you've started an explosion period. Once the hammer hits the back of that shell, an explosion occurs. But because the rifle barrel is strong enough along with the metal that it keeps it from exploding left and right and backwards, then all the explosion is pushed forward. That pushes the actual projectile or slug out of the shell, and now you have a system where the momentum that was originally zero is no longer zero, because you've got this 0.0300 kilogram mass moving this way at 735 meters per second. To counteract that, the rifle has to have exactly the same momentum in the opposite direction so that the total momentum is zero. We're going to do that and use that to compute the actual speed of the rifle, and that's what we mean by the recoil. Okay. Now, I want to remind you that the reason why we're doing systems here, I treated the rifle and bullet as one system. That's because it's very complicated to know exactly what force was applied to the bullet and what force was or projectile, and what force was actually applied to the gun. And in fact, trying to solve the problem that way would be a bit of a problem. But luckily, using conservation of momentum for the system, we know that the force that the shell and gunpowder applies to the bullet is equal but opposite to the force that the bullet applies to the explosion, or to the basically to the gunpowder and therefore the rifle. So those two are internal forces. We don't even have to think about them. Okay. So we're going to go again with conservation of momentum. So here's our solution. We're going to say again, P initial is equal to 7.0 kilograms times 0 meters per second plus 0.0300 kilograms times 0 meters per second is equal to 0 kilograms meters per second, which is just 0. Okay. Now, after the explosion, the final momentum will be 7.0 kilograms times the velocity of recoil, which I'll call VRC. This is all one dimensional again, so because we're shooting along a barrel, for instance, and then the velocity of the shell, or excuse me, of the projectile portion that was in the shell is 0.0300 kilograms times 735 meters per second. Okay. I'm assuming that my positive direction will be the direction that the bullet, that the projectile goes. So in this case, I'm going to get 7.0 kilograms times V recoil. Excuse me, I wrote equals there, plus 0.0300 times 735. That gives me 22.05 kilogram meters per second. So now conservation of momentum tells us that P initial is equal to P final. When I use that, I'm going to say 0 is equal to 7.0 kilograms times V recoil plus 22.05 kilogram meters per second. And of course, I use 2 extra sig figs there, or 2 extra digits there that aren't substantiated by significant figures, so I shouldn't use that. Now, what this means is now I got to solve for VRC, and what we get is V recoil is going to equal negative 22.05 kilogram meters per second divided by 7.0 kilograms. And of course, the negative is meaningful. If the bullet went off in the positive direction, this is telling us that the rifle will go off in what's called the negative direction. So I'm going to divide this 22.05 by 7, and that gives me 3.15. So the recoil velocity of the rifle is in fact about 3.2 meters per second. So that's not a small, I mean, that's not necessarily that small of a velocity. So that's something to keep in mind. In fact, if I said 3.2 and I did meters per second and I added that to 0 miles per hour, my calculator would convert that to 7 miles per hour roughly. So this is actually on the order of 7.2 miles per hour. Okay. So imagine 7 kilograms, which is about 15 pounds. So imagine a bowling ball. 15 pounds is a pretty heavy bowling ball. In fact, it's not uncommon for smaller, petite people to use 9-pound and 10-pound balls. So a 15-pound is pretty heavy. So imagine a 15-pound bowling ball hitting you at 7 miles per hour. That could do some damage, right? So when you see YouTube videos of people holding rifles, let's pretend this is a rifle, okay? And they're holding rifles like this, and they literally got their eye looking over the butt end of the rifle. That is not a good thing. That is going to be bad happenings because it's going to recoil and hit you right in your softy bits, which is like your nose and your lip and your eyeball and your that kind of stuff. So that's not a good way. You're supposed to, of course, hold a rifle with it butted up against the front edge of your shoulder, or maybe in that little area between your collarbone and your shoulder. But you're also supposed to have it up against you, not hanging out loose. If you have it hanging out loose, unless you're really ready for it, it's going to fire back with that same recoil velocity and then hit you. And yeah, that's enough to bruise you. So, any questions on that one? I'm going through this so fast. I don't want to kill you guys, but at the same time, it's nice being able to work this. I just want to make sure y'all ask me questions, even if I have to, not get through all my examples. I'd much rather you understand. So make sure you ask me if you have any questions. All right. So we got through 4 examples already. This is like awesome. I mean, I'm excited about it, but at the same time, if you're not learning, it's not awesome at all. It's the opposite of awesome. So no questions yet? I do have my chat open, so I can see that. Oh, and go ahead and type in your first and last name, so I have you for roll too. That'll help me. All right, now while you are chatting your first and last name for roll, I'll go ahead and say a bunch of words that y'all can ignore and move on to example 5. So example 5, this one's kind of neat. It says estimate the A impulse and B average force delivered by a karate chop when it breaks a board 3 centimeters thick. Assume the hand is moving at about 10 meters per second when it strikes the board. So this is one of those estimate type problems. Your book does a similar problem again, and my calculation actually comes up quite a bit different than theirs. The good news is when I did mine versus theirs, uh, they were within a factor of about 2 or 3. The rule of thumb when you're estimating is you and I should agree within a factor of 10. In other words, if I multiply yours by a factor of 10 and then I divide yours by a factor of 10, that should make a smallest number and a largest number. My answer should be somewhere in there. Or I could do the same thing with mine by multiplying it by 10 and dividing it by 10, making a smallest and biggest, and your number should be in there. So be advised when we're doing estimates, they're only supposed to be within a factor of 10. All right. This one's a little more complicated because we actually do have to make some assumptions. I will explain those as we go. So here's our solution. First off, I've got to tell you what impulse is. So if you look at Newton's second law, the summation forces is equal to dp dt. Again, that's really how Newton wrote it. If you multiply both sides by dt and then integrate, you get something called the impulse. And that's equal to the integral. In general, they normally say it's the major force or whatever, but I'm going to keep this and say the integral of f dt. And that's equal to the integral of dp, like this. All of that is right. All of that is, in fact, the impulse. Now, when you integrate this side, you just get delta p, which equals p final minus p initial. So the impulse really is just the change in momentum. That's a perfectly reasonable answer for what the impulse is. Most people, when they tell you they want you to calculate the impulse, they're actually wanting you to calculate that thing. But that's also the impulse, so it's okay, right? So I just want you to know that that also is the impulse. So this also is the impulse. So what are we going to do? Well, what I'm going to do is I'm going to assume the human hand is about 1 kilogram. So assume the human hand has a mass. Whoa, I decided to write that mass with 3 S's of about 1.0 kilograms, which is about 2.2 pounds, remember? Okay. And that it goes from 10 meters per second to approximately 0 meters per second in the thickness of the board. Okay. So our board has a thickness I'm going to call delta X, and that's equal to 3.0 centimeters. Okay. I know V initial is 10 meters per second, and I know V final is 0 meters per second. So what I can say is I don't care about all the forces adding up. Okay. I know that the biggest force around is going to outweigh all the other forces. So I can ignore all of them. And this summation of the forces from Newton's second law just becomes the karate chop force. So F karate chop, again, treating it like a one-dimensional motion, F karate chop is about equal to, and I'm going to put a bar over it to show that it's an average, it's about equal to delta P over delta T. So I need delta P, which is a change in momentum, and I need delta T, which is how long uh, it actually you're contacting or how long the person is contacting the board while they're breaking it. So I'm going to say delta P, which is P final minus P initial, is in fact 0 minus 1.0 kilograms times 10 meters per second, which equals 10, a negative, in fact, negative 10 kilograms meters per second is the change in momentum. Now, what we know is V is equal to, or at least V average is equal to delta X over delta T. So delta T could be delta X over V average. Well, if we assume uniform acceleration, or constant acceleration, let's change that. If we do that, then V bar then V bar is equal to V initial plus V final over 2, which would be 10 meters per second plus 0 meters per second divided by 2, which is 5.0 meters per second, which implies delta T. And now I'm going to get back to my purple. This implies delta T will equal 3.0 times 10 to the negative 2 meters, because a centimeter is 10 to the negative 2 meters, divided by 5.0 meters per second. This gives me 3 e to the negative 2 divided by 5 gives me 0.006. Oops. I'm going to say this is 0.0060 that's actually meters per second divided by or meters divided by meters per second. So that just gives me seconds, which is hopefully what I wanted. Or which is luckily what I wanted. So now I can calculate the average force, which I called karate chop, is equal to delta P over delta T. And that, of course, is 10 kilograms meters per second divided by 0.0060 seconds. So this gives me about 1,667 newtons, which is 2 extra sig figs than I actually have. So what we know is the average force of the karate chop is about 1,000, or let's call it 17. I'll call it 1.7 times 10 to the 3 newtons, which again, we can turn this into pounds. I'll quickly use my calculator. And I'll say 1700 newtons is 0 pounds of force. Add those together, and this gives me approximately 380, 380 pounds. So that's a pretty good force. And that is our answer to part B, if you will. And part A, we already answered. J, the impulse, is actually just the change in momentum, which was 10 kilograms meters per second. And that was a negative. Any questions on that one? No questions? All right. So this next one is really the big one that I wanted to solve. So it's actually going to take a little bit of work. I've got 9 minutes. That's not that big of a deal. But I want to show you basically how we're going to do it. So let me write here solution. Now we're introducing another concept that I didn't introduce last time, but there's a concept called a perfectly elastic collision. And your book is actually just calling that elastic, and that's fine. Elastic is fine too. Collision. And the perfectly elastic collision basically implies kinetic energy is conserved. So in addition to momentum, conservation, which gives us literally, I'm talking about 1D here. So this will be 1D collision. Okay. So what I'm going to have is mass A has initial velocity VA plus mass B has initial velocity VB. And since it's one dimensional, the plus or minus signs that can appear in the actual symbols is sufficient to just specify direction. So the momentum after the collision will still be ma, but this time it's the new velocity, which would be va prime, plus mb with its new velocity, which would be vb prime. Okay, so that's going to be equation 1. That's just conservation of momentum. Conservation of kinetic energy is this: 1/2 MAVA squared plus 1/2 MBVB squared is equal to 1/2 MAVA prime squared plus 1/2 MBVB prime squared. That's really what conservation of kinetic energy is, and I'm therefore going to call this equation 2. Now, with equation 1, I'm going to do some stuff. I'm going to get the MA on the left and the MBs on the right. So I'm going to have MAVA minus MAVA prime is equal to MB VB prime minus MB VB. Okay. I can make this a little better by writing this as MA times VA minus VA prime, and this one as MB times VB prime minus VB. Okay, let's call this equation 3. Now I'm going to do a similar process to equation 2. Notice, for instance, you can go ahead and cancel out all the 1/2 because all you have to do is multiply through the equation by 2. And now I'm going to get all the MAs on the left. So I'm going to have MA VA prime, or excuse me, MA VA squared minus VA prime squared is equal to, now the MB on the other side, notice that one's going to have the VB prime first. So I have VB prime squared minus VB squared. Okay. Let's call this equation 4. But let's make 4 a little more user-friendly. So what I'm going to do is say, actually, I don't want to write it above it. I want to write it below it. And in fact, let me go ahead and erase that, and I'll label it next. So what I'm going to do now is I'm going to say MA times VA minus VA prime times VA plus VA prime is equal to MB times VB prime minus VB times VB prime plus VB. Okay, and that's going to be equation 4. Now I can divide equation 4 by 3, and I think you can see what happens. Basically, we're going to get the VA minus VA prime is going to cancel out, as is the MA. So I end up getting VA plus VA prime is equal to VB prime plus VB. Or we can go ahead and simplify that a bit more by choosing to do basically get the velocities before on one side and the velocities after on another side. So what I'll say is VA minus VB that's what happens when I pull the VB over there. And then on the other side, I'm going to say VB prime minus VA prime, like that. And this is actually an equation we can use over and over again. In fact, your book, I think your book even tends to give it a number. Yeah, they call it equation 9-8. All right. So that's equation 9-8, and we can use that. We can start with that. And the only thing that has to be true is it has to be one-dimensional, and it conserves momentum, which means the total force acting on the system must be 0. And it has to be an elastic collision, which means the kinetic energy is conserved. So as long as we got that, we're golden. Now that we have that, we could actually solve this problem. For instance, problem A, it says, assume that both balls are initially moving at VA and VB. And what they want us to do is figure out what the speeds of the balls are after the fact. So we already know this one part of the equation, which is VA minus VB is equal to VB prime minus VA prime, which you can also reverse if you want them to both be AB. So it's VA minus VB. All you have to do is replace the right-hand side with the negative of the right-hand side in parentheses. So we can look at this and say, all right, well, we know since the billiard balls are all the same, MA, actually, let me write this in a different color. MA is equal to MB implies we just get VA plus VB is equal to VA prime plus VB prime. This comes from conservation of momentum. Okay, because it was originally MAVA plus MBVB equals MAVA prime plus MBVB prime. We just canceled out the masses and we're good to go. Now we also know that VA, looking back here, VA minus VB, VA minus VB is equal to the negative of VA prime minus VB prime. That's how I was telling you could reverse it. Just reverse the signs. Now, if we add these two equations together, we get VA plus VA is 2VA. And in this case, we get VA prime minus VA prime. So that's no VA primes left. And then we get VB plus VB prime. So that's 2VB prime. So what that tells us is that VB prime is actually now just going to be equal to VA. And that's one of our answers for part A. In other words, basically the velocity that the particle coming in initially with VA, now the other particle that it hit has that velocity. And if you subtract the two equations, then you get VA minus VA is 0. You get VB minus a negative VB, which would be 2VB. Doing the same thing on the right-hand side, you get VA prime minus negative VA prime. That's plus VA prime. So you get 2VA prime. And VB minus positive VB prime gives you 0. So in this case, we found that VA prime is equal to VB prime, or equal to VB. So now we see that they just trade velocities. Okay. So that was all part A. Actually, I wrote part B in there, but that's still part A. Any questions on that one? Now, in part B, we're supposed to assume VB is equal to 0. In other words, it started from with VB sitting still. In that case, we start off with VA is equal to VA prime plus VB prime. And we still have the other equation, which would be VA. Normally it would be minus VB, but that's 0. And that's got to equal negative VA prime minus VB prime. Again, we can choose to add them or something along those lines if we so desire. If we subtract them, we get VA minus VA, which is 0. And then on the right-hand side, we get VA prime minus negative VA prime, which would be 2VA prime. And we get VB prime minus positive VB prime, so that's just 0. So this tells us that VA prime is equal to 0. If we add them, VA plus VA would be 2VA. And then on this side would be VA prime minus VA prime. So that gives me 0, but I get VB prime plus VB prime, which would be 2VB prime. Okay. So in this case, we find that VB prime is just going to be equal to VA. So what we've discovered here is that they still are trading velocities, but one of them had initial velocity of 0. So now the one that didn't have initial velocity of 0 comes to a stop and the other one takes off. This is exactly what you've probably seen playing pool. Often you'll hit a cue ball and it'll hit the 8 ball and then the cue ball will stop. And I've been rushing trying to get this done by 6:20 and just realized the class doesn't end until 6:40. Any questions on that particular problem? Okay, so that's a nice little technique that allows you to repeatedly, for instance, use that expression that we just derived, the VA minus VB is equal to negative left parenthesis VA prime minus VB prime close parenthesis. That's an equation we can use over and over again. Uh, in this case, we used it with equal masses. And example 9-8 of your book, they do it with different masses, and you can get a more general expression, which is really, really nice. And in fact, if you look, your book says problem 34 allows you to work out the most general case for a head-on one-dimensional elastic collision. So let me show you what I mean by that, or at least let me point it out for you. So I'm going to do this and say C problem 34 from chapter 9 to derive the most general results for a one-dimensional elastic head-on collision. Okay. So that's what I'm going to tell you to do. Now I'm going to go ahead and attempt to work yet another problem. So let's imagine, for instance, that one target, or let's say the VB prime is going to be 0, or excuse me, the VB is going to be 0 again. So we're going to work another example. I think this would be example 7, maybe. Yeah, example 7. So what we have here is a mass MA moving with velocity VA is going to run into a mass VB, which is sitting still. Okay. What's going to happen after the collision is that we're going to have MA moving with a velocity VA prime. And I'm just going to draw everything like it's going to the right. We don't really know what's going to happen, but that's going to be VA prime. And MB is going to be moving with VB prime. Okay. So first off, solution. And notice what we're looking for here is VA prime equals question mark and VB prime equals question mark. So conservation of momentum. For this one, it's just going to be MA VA is equal to MA VA prime plus MB VB prime. Okay. So we can do something with this. Basically, what I'm going to do is group the MAs together. So I'm going to say MA times parentheses VA minus VA prime is equal to MB times VB prime. So that's one equation. Now I'm going to use equation 9-8, which, by the way, was, recall, let me write it in red right here. That's actually, there's no masses in it. That is VA minus VB is equal to the negative of VA prime minus VB prime. In this case, we're going to choose VB equals 0. So what that gives me is just plain VA is equal to, well, actually, no, I think I want to save it. I think I want to solve it another way. I'm going to take this and use that 0, and then I'm going to say that gives me VA. Actually, I'll keep on working it in red. That way it won't be so confusing. So VA is equal to negative VA prime plus VB prime. What I'm going to do is solve for VA prime, and that's going to give me VA prime is equal to, pulling that to the other side, VB prime minus VA. So now I'm going to put that up there and say VA prime is equal to VB prime minus VA. So that gives me two equations that I can use. Now, because I've used that, I've actually made use of conservation of conservation of kinetic energy as well. So now I can actually try to do something with them combined. I can take, for instance, the VA prime and plug it into the other equation. So let's say plug VA prime into MA VA minus VA prime equals MB VB prime. When I do that, I can get MA times VA minus MA. Now, in place of VA prime, I'm going to write VB prime minus VA. Oops. Like that. And then on the other side, I'm just going to write MB VB prime. Now I can see that I have only one unknown with the prime symbol in it, and that's VB prime. So I can write this a little further. I'm going to start on the left-hand side so I can have more room. I'm going to say MA VA minus MA VB prime. Minus minus becomes positive MA VA equals MB VB prime. So now I'm going to get the VBs all on the same side. So the way I'm going to do that is take my MA VA and leave that on the left. And in fact, the MA plus the MA VA, like that, those two add to give me 2 MA VA. And then when I pull the MA VB to the right, what I'm going to get is equals MA plus MB times VB prime. In other words, I went ahead and skipped the step of factoring out the common VB prime. And now from that, I can get that VB prime is actually going to equal 2MA over MA plus MB, all of that times VA. Now, you might notice that looks a lot like the tension equation we had for the Atwood machine. Oops. So looks like tension for Atwood machine. The reason why I say that is that's what allows me to keep remembering this result. In the case of the Atwood machine, you had 2 MAMB over MA plus MB, and then it was, of course, times G. But you could imagine one of those G's was that G was being multiplied by one of those masses, so it looks about the same. And that is the actual answer we're going for. Now that we have that answer, we can go ahead and solve for VA prime as well. So VA prime, let's got a couple more minutes. VA prime, we already found, was equal to VB prime minus VA. So I'm going to say VA prime is equal to 2MA over MA plus MB times VA minus VA. So what I want to do is get a common denominator. This one already has a denominator of MA plus MB. However, this other one has a coefficient of -1. So what I'm going to do is multiply it by MA plus MB over MA plus MB like that. And then remember, I did factor out a VA from both of those already. So now we can just combine them and say VA prime is equal to, now I have one common numerator, that is 2MA minus MA. Remember that minus sign is in front of a fraction, and the fraction bar acts like a parenthesis. So that minus sign has to be distributed as well. So it's minus MA minus MB. And all of that divided by MA plus MB, and then all of that multiplied by VA. 2MA minus MA is actually just equal to MA minus MB over MA plus MB, and all that's times VA. And notice this one looks exactly like the acceleration from the Atwood machine. So I'm going to say now that VA prime, which was what we were trying to solve for, is MA minus MB over MA plus MB. All of that times VA. And I'm going to box it off in a little red box. And I'm going to say, looks like the A for the Atwood machine. Anybody have any questions on that? No questions? All right. Well, we only have 2 minutes left of class. Uh, I could probably fit in a center of mass calculation, but I'm not sure y'all would get very excited about it. Let me do it real quick just for the heck of it. So let's imagine this is our x-axis, this is our y-axis, and let's imagine we have a two-dimensional object like this, okay? It has a mass, big M, and let's say this is a width W, and this is a height H. And I'm going to say mass is uniformly distributed. And that means that sigma is the mass divided by 1/2 h times w. Okay. Now you can, for ease, you can realize that this equation for this line is y equals, notice the height was h and the rise was h and the run was w, so it's going to be h over w times x, and the intercept is just 0. What I want to calculate is x center of mass, which equals the integral of x dm over the integral of dm, and dm is going to be sigma dA. So when I go to do this, I need to make sure a doesn't vary very much over the integrand. So what I'm going to do is put a little rectangle right here, and this width is dx. And then, of course, the height is y of x. So if I go to calculate the integral of x dm, what I do is I take the integral of x and then I multiply it by sigma times dA, but dA is in fact y times dx. Well, y is h over w times x, and then times the dx for dA. So you can see from this, we're going to get h sigma over w times the integral of x squared dx, and I'm going to integrate from x equals 0 to w. That's going to give me h sigma over 3w times w cubed. Now I've got to do the integral of dm, which is just the integral of sigma h over w x dx, which is going to be h sigma over w times the integral of x dx, which equals h sigma over 2w times, again, 0 to w, times w squared. So xcm is just going to be equal to sigma h over 3w w cubed. Of course, that's going to make some cancellations, and sigma h over 2w w squared. Again, that's going to make cancellations. This is going to become 2, and that one's disappearing. This one's going to become 1, and that one's disappearing. This one's going to cancel out completely with this one. This one's going to completely cancel out with that one. So ultimately, all I'm left with is 2/3 of, now I've got a w squared over w, so it's 2/3 w. And that, by the way, is the rule for triangles. It's always 2/3 of the way to the widest part. The y center of mass formula is about the same. Y'all can work that out on your own, but I just wanted to give you one example. I did go 2 minutes over. I apologize, but hopefully that helped you a little bit. So everybody's free to go. If you didn't already put in your name, your first and last name in chat, please do that. Other than that, you're free to go, and I'll wait for the last person to leave in case anybody has any questions.
Thank you. Have a good one.
Thank you. Thank you for coming, everybody.
When the what other class you have for like in class, like in person on Monday?
You wondering when I have the face-to-face class?
Yeah, the face-to-face class.
My lab meets at 9 a.m. on Tuesdays for that class, but the lecture meets at noon on Tuesdays and Thursdays.
Noon Tuesday and Thursday.
Or excuse me, Monday and Wednesday. Sorry, I don't know why I said Tuesday. The lab meets at 9 a.m. on Monday, and the class meets at at noon on Monday and Wednesday. Sorry about that.
Monday, Wednesday, 9 a.m. Yeah.
The lab is 9, and then the class doesn't start till noon.
Like what time
Yep.
during noon?
You're welcome to come anytime you want. You can come to the lab too, just to get credit or to get help. Also Wednesday, I have a different lab, but you can still come get help because it's just a 242 class, but you can still get help in that one as well.
What time is it during noon? Is it 2? Coast
The
time
242 class, the lab starts at 9 as well, but it's on Wednesday instead of Monday. But the lecture actually doesn't start till 2. So if you
2.
wanted to come to the 242 class, you could do that, but
Yeah,
241's at noon.
got you. Okay,
All
thank
right.
you.
See you,
Right.
Kim. Have a good one.
You too, sir.
Okay. Not sure that did not blow them apart because they did not reply much.